moving on to our next portion of this chapter, which will lead us into uh, a pretty good hands-on activity that we'll perform next week. And we're on page 312. Okay. This next section in chapter 9, dealing with what we see limiting reactants, and it talks about percent yield. Now, those are two different concepts that we will approximately get to the percent yield part probably next. Well, of course, it's going to be next week. So, how does that sound familiar from what we did last semester? We did. It was percent composition. So remember, we're doing reaction stoichiometry as opposed to composition stoichiometry. They are related, but they're different concepts, because with every problem-solving, I want to say not activity, but problem that we've dealt with, you had to have what? Well, whether it was a mole to mole, a mole to mass, or a mass to mass, you had to have what to convert from what to the other. Well, true. You had to do something first before you could make the conversions. Yeah, you had to have a chemical reaction. So this is no longer composition stoichiometry. We started reaction stoichiometry. Okay. So yes, there's a sample problem on page 313 that I would suggest that you go ahead and work through. And this is going to be similar to where, yes, you have to have a balanced chemical equation. And one of the aspects that we work on is when we say a limiting reactant. Let's say, for instance, for some reason, you're going class by class at this time, say, well, the 6th-hour class is going to be, what would you want to pick, a volleyball or a basketball team? Okay, so we're a basketball team, okay, and you can pick whoever you want to be as captain and whatnot, and we've got the lead late in the game, okay, we're ahead by 2. And we're within the last minute. Okay? You can picture a limiting reactant similar to that of a weakest link. Okay? So what people, or not combating teams, but what's the word I'm looking for? Other competitive teams at this time of day, okay? And whoever it is that we would be playing against, okay, we need to foul someone. Who's the weakest link that we've got? Maybe it's myself. Maybe it's something that you can pick, and you can say whoever. Okay. So why is it that another team would pick to foul one of, because you raised your hand and everyone else said him, so which one of them two? Okay, so why would they pick to foul Cole then? Okay, so what might, it has nothing to do with tackling, okay, because what are you probably going to do when they foul us? They want to pick the worst, what? The worst free throw shooter, or the weakest link. So that's one way you can look at limiting reactants. What it means is we're dealing with the left-hand side of the arrow, or the reactants, and what limits what you can produce. It doesn't, the reactions will continue to work through, but the limiting reactant limits how much you're actually producing. That's what that means, and that's why you would calculate limiting reactants. The reason, there is a very long problem. Let's see if I can, I'll just read it to you. I think it's in the back of the chapter. And It's one that will be assigned to you, not today, but perhaps tomorrow. Just follow along on what it sounds like, okay? But if you do want to read it, it's problem 27 on page 321, okay? And it goes on to state, the energy used to power one of the Apollo lunar missions was supplied by the following overall reactions. And they give you the balanced chemical reaction to where I think N2H4 is hydrazine, and then the next reaction I think is dimethylhydrazine, and then the third one is dinitrogen oxide, okay? And when you combine them three, you're going to get on the product side some nitrogen, some carbon dioxide, and water. Now, some of that would make sense from combustion reactions. We always knew you're always going to get what byproducts when fuels are burned? Carbon dioxide and water. Okay, but there's some nitrogen given off in this aspect as well. So what it's going on to ask is, for the phase of the mission when the lunar module ascended from the surface of the moon, a total of 1,200 kilograms of hydrazine was available to react with 1,000 kilograms of dimethylhydrazine and 4,500 kilograms of nitrous oxide. So what they're saying is one of those is considered as the weakest link, okay, because it will run out first. So like they're picking the worst free throw shooter to foul. Here, if you were one of the NASA technicians, I don't think that sounds right, maybe scientists or engineers, actually, a chemical engineer, you would want to make darn sure you had enough of the correct gas. Notice they're not saying 1,500 kilograms of this substance, 1,500 kilograms of this substance, and 1,500 kilograms of this. That would be a disaster. And that's why you see that 4,500, 1,000, and 1,500. But what's still going to happen is, just like in a race, someone's got to come in last. Okay? And just like in any game, you got a winner and you got a loser. You can even break that down to any call that's, any call that is made. At least if it's made, if you're thinking of Los Angeles and New Orleans, and of course that is just totally, well, I wouldn't say taken over social media, but you can see so many posts. I wouldn't say mocking that, but it's so easy to look back in slow motion. It's really obvious, but I think people still need to not lose fact to the idea that that game is moving so fast. It doesn't necessarily have to be that game. It's any NFL game. You've got players running in all directions. You're just not going to see every play that's made. And you even ask the coaches and the quarterbacks, and they say, it's unfortunate. It just wasn't called. And that's what they're saying at a press conference. I'm sure there's a lot more to that which they could say, but and again, it's just rather unfortunate that had happened. So just think in this case, you forget to carry a number as a chemical engineer, and you don't have enough of the right reactant up there, and the proportions don't produce enough energy to bring that lunar module back to Earth. A little more high stakes, yes. I'm just curious. Enlighten me, you two. Are you just writing, all I hear is blah, 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 blah? Oh, well, you don't have to tell me. I was just guessing that it said blah, 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 blah. No. Hi, Grace. How was your day? Oh, yeah. Yeah.
I said we're going tonight, but she said maybe. And I said, I will ask your mama. And she
Oh.
said, we will see what happens. And I'm like, no.
You just couldn't wait till later.
No.
All right. Anyway, so let's get back to the important stuff, not what you're doing. All right. So back to page 313. And that's why, and none of us in here, I don't believe, but maybe the exception of one, may become a chemical engineer. Okay? I don't know. No? No. Okay. Okay. All right. So, and of course, you might be asking, why do we got to do this? And, it's not that I can come up with an answer either, but sometimes I think it can be attributed to if you're going out into society, if your supervisor or boss tells you to do something, you better do it. You can say, well, you all have choices. You can not do it and just be prepared for the consequences. So whether you like it, don't like it, that's what we're doing. So hopefully we can see some of the rationale behind some of these problems is what I'm getting at. Okay, so page 313, practice problem number 1. It says some rocket engines use a mixture of hydrazine, and it's not that I have that formula memorized, but from year to year you tend to remember some of these names of compounds. So N2H4 is hydrazine, and hydrogen peroxide as a propellant. Now, this is not the same one we just talked about. Okay, this is a different reaction. The reaction given by the equation, or excuse me, the reaction is given by the following equation. And they're really nice to you, how or why. It's given to you, it's written out, and it's balanced. You should think that's so lucky. Okay, one of the ways you can look at this, you can say, well, I got a 50-50 chance. It's going to ask for, well, what's the limiting reactant? And usually what happens is they'll also ask how much of a certain product is formed or how much of an excess reactant is left over. It's probably more common to ask for how much of a certain product is formed. And you can't just take one substance, what you start with. You have to use the limiting reactant because which one runs out first? The limiting reactant does. It's still going to proceed, but you're limited on how much you have because it runs out first. So we are ahead by 2, and the other team has just fouled our free throw shooter. Okay? There's still 30 seconds left. 2 shots. How many are you going to make? So, how does that have to do with a free throw shooting motion? Oh, okay. How about iron will? Iron arm. Okay. Okay, just like the moon is sugar, 8%. Yeah. Okay. All right. So part A, number 1 on page 313. Which is the limiting reactant in this reaction? We have 3/4 of a mole of hydrazine is mixed with half a mole of H2O2. Okay. So I think there's a couple different ways that you can solve this, but if you're given the amount in moles, I always describe it, it's kind of like playing Battleship, okay? So you two are playing Battleship against one another, and what is it, you say like E4, and then you say hit or miss, so it's kind of like you're firing across to him, okay? So you're firing towards this direction, and whether it says hit or miss, doesn't sink anything, then you say, well, I'm going to go with D10. So you're firing back, okay? And that's kind of like what we're doing with these reactants. So what we do is write these down. We've got N2. Was it H2 or H4? Okay. And then we've got hydrogen peroxide. Okay. And then that gives us what? Water? Or I think this had a 4 and this had a 2. And that was given in the equation, correct? Okay. So how much are we starting with of the N2H4s? Half a, no, it's 3/4, correct? Okay. Then this was half a mole. So what we mean by playing battleship with this is how much you have of each substance. Remember, moles are counting units. Just like you take a tape measure, run across this table. Who wants to say 96 inches every time? And it's more convenient to say 8 feet. You're dealing with smaller numbers. So again, the 8 feet is a counting unit for how many inches you would have as well. So what we see happening here, where the battleship comes into play, is this fires back at, fires at this, then this one fires back. That's what we're talking about when we're playing that battleship. Okay, so you're converting moles of this to see how much of that is required. Okay, and again, I get to cheat and look at the book, but it just gives you an answer. It doesn't tell you how to find it, right? No, it just gives you the answer. But we said, if worse comes to worse, what could you do? Just guess, right? But then what about if it's asking for how much excess is left over? Well, then what do? You guess again? Well, if you don't know how much you used up, how do you know how much is left over? You're hoping for a lot of luck. That's correct. Okay. So, again, we can make some predictions and see. I get to say hydrogen peroxide is our limiting reactant. And don't go by just because there's a 2 there. Don't go by that. Could be. Okay? So the best way is to keep solving these the same way, because then you know are always going to be right. Just like when we're converting this to grams, if you always carry that 2, it's going to be a good habit, and you're always going to remember to double it. Okay, so we've got 0.750 mole of N2H4, or I'm just going to put HD for hydrazine. Well, maybe I better write it out, or else I'm afraid you may get confused on that first time around. N2H4. Sometimes some people are, I'm going to try to sound smart by throwing out all these organic names. Oh, the students, they'll really be impressed. Man, they're really smart. They know all this stuff. Well, maybe yes, maybe no. I'll let you decide that. Okay, so we got 3/4 of a mole of this N2H4. So again, it's kind of like playing that battleship. We're going to shoot this at hydrogen peroxide to see how much of that is actually required. So how do we cancel this out, the N2H4? Okay, so we have a mole of this on the bottom. Okay, and just like the first set of problems that we learned this semester, it's just a 2-step problem of moles to moles. So we want to see, we're going to put moles of what up top then? Right. Now, we're not doing anything, it doesn't say anything about the products over here. So we're just staying on this side. Okay? It's a funny looking H. There we go. That's better. Okay, we got a mole ratio. What does that mean? Look back at your equation. Okay? So, what that means is that gives us what? And what I like to do is when you're doing these is somewhere either up above, down below, or right to the side, just put these. What do you suppose that is an abbreviation for? Required, okay? So, this is how much is required. So, now we can say that $1.50 is required. Well, how much money did you have to spend of that substance? 75 cents or 50 cents? You had 50 cents, okay? And what you got to remember is compare what's required, 1.5 moles of H2O2 compared to half a mole of H2O2. Technically, we could stop there. But should the problem like this one goes on to ask, no, it doesn't say that. So, oh yeah, it does in step B, how much of the excess reactants left over? Well, you won't know that until this fires back at that one. So then what you're going to have to do is the same process and then change that from hydrogen peroxide back to N2H4. So hopefully that example or analogy had made sense. You're firing this at that to see how much is required. Then this one fires back to see how much of that is required. So 0.500 mole of H2O2. And again, we've already found our limiting reactant technically. But there's not enough than what's available. Okay. So some of these we like to use this cost analogy, and in this we say, well, we've got 75 cents. How much does it cost for this reaction? Okay. So then what we would look at is again a mole to mole ratio, but we flip-flop our reactants to put H2O2 on the bottom, then N2H4 on top. Okay? And again, you're just canceling out your factors, just like we've been doing, I want to say, for the better part of all year long, really, going all the way back to August, when you did just even molar mass calculations, or just making grams to moles, whichever way makes more sense. So we got a mole ratio. What does that mean? Back of the equation, 2H2O2, which goes down here. So now a half divided by 2 gives you what? So then this is what is REQ. Okay? 25 cents is required. Well, how much did we have of that to begin with? 75 cents. So that means you use this as a comparison. You have to calculate how much is needed first. Okay? So that means we needed $1.50, but we only had 1/2. So that's how you determine the limiting reactant in this process. Now, there's a different way that we can look at solving these, but we won't have time for that today. Okay? So I've seen some of you students more than once look up at that wall to see how much time is left. Must not be fun in here. Am I correct? Is it the fun or looking at the wall? Or neither? Neither. This class isn't for everybody, is it? I think anybody would agree. Okay, but if it was for everybody, there'd be more filled desks, right? I'm sure you tell your classmates what they're missing in here. And well, So then when we make this analogy, then what I would suggest, you go up here and do whatever it is that you have to do to say, okay, this is our limiting reactant. Okay? Because everything you calculate on the right-hand side is based off of how much you have of your limiting reactant. Remember when we had said you don't want to be the chemical engineer that puts too short of a substance in for a reaction to take place. Again, that lunar module, if it didn't have enough of the limiting reactant, well then what's given off as a byproduct isn't enough. You might think, well, who cares how much water is given off? But at the very basics, when them bonds are reformed, if you remember from physical science, when these bonds are broken and when they reform, what's given off? Starts with the letter E. Lots of energy is given off. So, if you're supposed to be producing, let's say, 10,000 kilograms, but you short your limiting reactant and now you're only producing 7,500 kilograms, you've got a problem. Okay? All right. So like letter B goes on to state, how much of the excess reactant in moles remains unchanged? Well, if this is the limiting reactant, this must be which reactant then? The excess, just like the question's asking. So we had 75 cents to spend. How much did we spend? We only spent 25 cents of it. So that still leaves us with a half. What does the book say? Hot dang, 0.500 moles of N2H4. Okay? So now it goes on to ask how much of each product in moles is formed. Okay? So then, which one do you think is the most important part of this side of the equation? The excess or the limiting? The limiting by far. So what that means is anything on this right-hand side has to be based off of what your limiting reactant was. Now, looking at this, I don't know if you can answer it, but what can be a very common mistake that students will make when they're trying to find how much of a substance is made on the right-hand side? How could they possibly start with a wrong number? Yeah, what happens is, remember, a good idea to write these out is to show you how much you actually have. Because here, you're calculating what you need. So, the last thing you're going to want to do is say, oh, well, since H2O2 is our limiting reactant, well, I've got 1.5 of that. Is that correct? No, you do not have 1.5. You only have 1/2. So that's a common mistake that's made. It's human nature. Okay? That's why we work through these. So when it comes to mistakes, two things we work on. One, you learn from it, and two, you hopefully don't repeat it. But again, it's human nature. It's going to happen. Okay. So what that means is, again, I should say what it means is I get to cheat again. I get to say 1/4 of this, and then 1 of this. They don't have the answers in the margins in your textbooks. I thought they possibly did. Oh. Schnucks, right? Okay, so let's go ahead and quickly take a peek. We'll just do, which one you want to do, water or nitrogen?
Water.
Okay, so I heard water first. So again, you've got 4 different numbers you're looking at. Which one are we going to start with? No. No. We just went over this. And again, we're making those mistakes already. And it's a learning experience.
What is
No. Well, that's the answer. But I'm saying, how do we get to that? I said we're only going to pick one. How much of it, though? Right. Right. Where are you getting one from? That's how much in moles is produced. We're showing you how you get that answer. Remember, I said I can cheat. Oh, I thought you said 0.25. Okay. This is recording. I can go back and look. Yeah, you're probably right. How many of you believe him? Then, okay, well, all right. Okay, so 0.500. Okay, so what we see happening, okay, how do we get rid of this mole? Well, a mole ratio then. So where do our numbers go? 4 on top? Sure? What's 4 divided by 2? And 2 times 0.5? Okay, there we go. So I said, yep, I can cheat. I could look at the answer. That's how you get 1. You know, otherwise, what does it mean if I just say, well, that's how you get 0.25 and 1? You say, well, how do you get 0.25 and 1? Well, this is how or this is why. Okay? So tomorrow we will continue with calculating limiting reactants. We will not be throwing percent yields, I don't believe, until Thursday. Okay? So we may go over some of them on Thursday. Okay, we'll pick up with this information tomorrow.